I believe that we can start. So, welcome everyone to our usual Wednesday seminar. And today we have a local speaker, Philippe, who will present on the radiation, fluid gravity, and the flat limit.
Okay, thank you, Sergey. Okay, thanks everyone. This is a manuscript that we upload to archive a couple of months ago. Collaboration with Gabriel Arenas from Tsinghua University in China, Luca Ciambelli in Perimeter Institute, Wei Zhenjia from Hong Kong, and David also from our institute. Okay, so I will just motivate the problem using holography. How holography nowadays has been also trying to be extended for asymptotically flat spaces. Then I will discuss a bit of how gravitational radiation plays a key role into describing quantum gravity for this kind of spaces and how we can extend the notion of radiation to include cosmological constant, which is way more subtle. Then I will discuss how the fluid gravity correspondence, which is a corner of the ideal CFT, can be used to describe uh, radiative spacetimes in the bulk and how induced dissipation in the boundary. And then at the very end, we're going to take the flat limit of the quantities that we were able to describe. Okay, so the ideal CFT correspondence, of course, I think you all guys is a correspondence that was initiated well, even before Maldacena, the holographic principle was described by Saskin and Tuff. But Maldacena in 97, he gave a concrete example on how gravitational theory can be described in terms of field theory and vice versa. So he particularly showed that the low energy limit, well, the effective low energy limit of a string of superstring theory, type 2b supergravity, is actually dual to conformal field theory, particularly the super young mills, when the type 2b theory is on a ADS5 cross S5 background. And it has been very well, it's one of the most cited papers on the archive in an area and has been very fruitful the last 20 years. Uh, Nowadays, it's not even about the string theory, I will say. Like people even just work in pure ADS gravity and try to do holography and still found amazing results, even without relying on computation of the string theory. Uh, Particularly allowed to, because it's a weak strong correspondence. This allows you to describe strongly coupled field theories at the boundary of ADS, but also gives you a non-perturbative definition of quantum gravity on asymptotically ADS spacetimes. So the dictionary is basically that if you have a field in the bulk that will sort an operator in the dual CFT, and if you have a local symmetry in the bulk, will remap to a global symmetry in the boundary. Yeah, also I didn't mention, but it's important that conformal symmetry arise in this field theory in the boundary. The holographic coordinate, we'll refer to as a radial coordinate, actually induce a Hamiltonian problem in the theory, meaning that it's actually the energy scales of the boundary theory. And when you go to all the way to the boundary, you get a critical point when your theory becomes conformal. Also, if you want to induce temperature, you want to have a thermal CFT, you need in the bulk to have an non-extremal black hole. And we would like to know what happens if you have radiative spacetimes in ADS to even complete more the dictionary. Uh, of course, one will think that you will have non-equilibrium dynamics at the boundary, and that's what we're going to try to see using the fluid gravity correspondence. Okay, but we do not live, according to data, we do not live on asymptotically ADS spacetime. We live in a asymptotically flat space, or, well, this novel of 2010, sorry, uh, also show that maybe we are living on asymptotically at the zeta space-time, even in the past infinity and future infinity time, future infinity. So it will be nice to see if we can define quantum gravity using holography, but for these kinds of space-time, for the zeta is really subtle. I think there is basically no progress on that. It's very difficult to discuss the zeta. The flat limit was discussed even in the very first years of the DSFT after the Maldacenas paper by Saskin. The decoupling limit breaks, you have a problem, the two constant goes to infinity. Then there's not much to do, the boundary theory becomes ultra non-local. So it's hard to take flat limits of this kind of, starting with the original Maldacena. Nonetheless, a paper appeared like 2 months ago or so, maybe less, by Fontanella and Payne, in which they give a possible resolution, in which were able to take the flat limit of the original Maldacena in type 2b supergravity and in the super young theory finding agreement. Okay, but there are another proposals of holography which do not rely on string theory, basically started by Strominger. This is more kinematics, but it's basically that if you have an in and out state, this corresponds to correlation functions on a celestial CFT. So you have a two-dimensional hologram plate, which is the celestial sphere or the sky, if you want. So if you have a scattering process in the bulk of Minkowski space or asymptotically flat, you will find a conformal field theory with non-trivial correlators. This is already like 10 years old. People still do not know much about the celestial CFT. There is not much on partition functions because it's basically argued by kinematics and symmetry matching. But still, we have learned a lot. For instance, this is the well-known Strominger, Padersky infrared triangle, in which people have been able to, using, for instance, how to relate asymptotic symmetries of Minkowski or asymptotically Minkowski space with subtheorem using word identities, the subtheorem with memory effects by Strominger-Chigoedov using Fourier transformation, memories with asymptotic symmetries, meaning that the super translations relate different vacua in the bulk. Also, if you go to the subleading order, there is even more going on. You have subleading subgravitron theory, you have the spin memory, you have the kick velocity reflection memory. So we have learned a lot purely studying this celestial CFT program. And also there has been a more like recent advance on something that is called Carrollian holography, a different approach, which is based on the fact that the asymptotic symmetry group at null infinity of an asymptotically flat spacetime is the BMS4 group. So BMS stands for Bondi, Mercer, and Zag. And they found that so when you go, you find the asymptotic symmetry group of Minkowski spacetime, you will expect to see something like Poincaré. This was in the 60s. So you expect Poincaré, but you actually get like an infinite dimensional enhancement. So you have Lorentz group, semi-direct product with super translations and super rotations, okay, which are basically transformation like angle dependent transformation of time and angles. So that was something it's like very similar what happened in ADS3 when you go to the asymptotic symmetry group. This found by Geno. They found a Virasoro, two copies of Virasoro algebra, which is infinite dimensional as well. And this group, why it's called Carrollian, because Duval, Gibbons, and Horvath, they found that it's actually isomorphic to the conformal Carroll group. What is the conformal Carroll group? It's a group contraction of Poincaré. So you take Poincaré and you rescale the generators and then take the C to 0 limit. So it's the ultra relativistic limit. And you found this group. So the light constraints here, as you can see on this picture. And that means that you don't have dynamics on this kind of theories. In the boundary theory living at null infinity. Why it's called Carroll, this was found by Levi Leblanc in 65. Sorry for my French. Uh, and he called it Carrollian because there is a story of Lewis Carroll when Alice is here in the rabbit hole and in this race, and the queen tells her like, "You can run as fast as you can, but you're gonna stay in the same place," or something like that. I don't. So that's exactly what happened on this series. The speed limit is actually zero, the ultra relativistic limit, and that's why they're called Carrollian. So you have two approaches for describing holographically asymptotically flat spacetime. So which one is the correct? And actually, they're both the same. This has been discussed in these new papers by Laura Doné and Adrian Fiorucci and Roman Rusiconi, in which they bridge both approaches. So they show that the word identities on a Carrollian CFT, if you perform a suitable integral transformation, you will find the word identities of the celestial CFT that has been found before. And actually, they also show that the word identities of the Carrollian CFT are exactly the BMS flux balance law. So the bonding mass loss formula and how the angular momentum aspect change. But also, there was a new paper some months ago by Ferrucci, Vilate, Petropoulos, in which they show that if you start with a theory and you ask for Carrollian diffeomorphism and Bail invariance, you will find exactly the BMS flux balance law. So the only thing that in this paper was crucial that the Carrollian CFT was sourced, meaning that in the bulk you have radiation. So you have gravitons going into the boundary, meaning that you have a non-trivial bonding use. So radiation plays a key role in both in celestial because you want in and out state, you want the scattering process, and also in the Carrollian side because otherwise it's trivial. You're just discussing flat space holographically and there's no much going on. And if you want to both approaches to match, then you need to have radiation. Sorry. Okay. So how you describe radiation? There are many approaches. I'm not going through the Bondi gauge because it's very the Bondi Sachs formalism. But if you guys have a question, please. So you can use the weak field approximation, which is what people do. Like for instance, Xavier, I have seen write this kind of equations many times, in which you expand around, you linearize around flat space, and then you compute quadruple moments and its third derivatives to get the power, etc. You can also use the Newman-Penrose formalism, which describes the strain or how the strain changes by this invariant. You can use the Bondi-Sachs formalism, which basically is a way to describe asymptotically flat spacetime. It's like the Fefferman-Graham gauge, but for flat space. There are more gauges, of course, but it's like the one most used. Why? Because Bondi and Sachs, they study in detail. They realize the BMS group, of course, and also uh, all the gravitons or all the information of radiation is encoded in a tensor, which is called the shear tensor, which is the CAB. And his time derivative, use the retarded time, is called the News tensor. So they show that if you have a non-trivial News tensor, then you have a radiation. And they show that the energy of a system in the bulk that contains a news will decrease in time due to this radiation that is going to null infinity. You can also use the post-Newtonian approximation, in which you expand around a small parameter and go beyond this weak field approximation. This is like the most famous one. But still, all of these ones are for asymptotically flat space, no cosmological constants. So what I would like to understand is how to get radiation in ADS, how to connect this with holography, and how to take flat limit of that to see if we can use some results or use the machinery of ADS-CFT and take flat limits. So a new criterion has been proposed, actually a criteria has been proposed for any value of the cosmological constant by Fernandez Álvarez and Zenovilla, sorry, I forgot here. So Fernandez Álvarez was a student of Zenovilla, was his PhD thesis this year. And what they did was to use a tensor that has been forgotten in years, which is called the Bell-Robinson tensor. So the Bell-Robinson tensor is this tensor over here, which is basically like Weil plus Hodge-Weil, dual of the Weil times dual of the Weil. Sorry, I'm missing a star here as well. Star means Hodge dualization. And this tensor was described in the 60s by Bell, also and Robinson separately. It's kind of a weird tensor because it's just like the stress tensor, total asymmetric, it's traceless, is covariantly conserved, so you can describe current, and also has a component which is positive definite. It's a time-like component which is positive definite, so allows you to describe fluxes of something. But it doesn't have the units of energy, it has the units of tidal forces or tidal energies. So they call it the energy that the Bell Robinson gives. It was called like super energy by Bell. Then Desert called it like ambiguous energy or something. They didn't know what to do with this tensor because it was very similar to the stress tensor and you can describe. But then Zenovia in 99, he showed that actually these super quantities, super energy, and whatever are related to quasi-local energies. So the Bell-Robinson tensor allows you to describe energy or other kind of conserved quantities in sub-regions of space-time. So what they did, they used this tensor, which carries the information of tidal forces. And the thing is that this one decays too fast because it's Weyl square and Hodge Weyl square. Well, not square, but has the product. So what they did, they used Penrose conformal compactification. So they use a Weyl transformation on the metric. This is called the unphysical metric. This is the physical metric, where this omega function dictates where the conformal boundary it is, meaning that you have to choose such that omega is zero in that point, and the limit omega to zero of the unphysical metric exists. Unphysical metric exists. So this defines a conformal class of metrics. And uh, okay. And now the thing is, what you do, for instance, in electromagnetism, you do the same. You have a stress tensor, you contract it with a time-like unit vector, right? Then you have the electromagnetic, it's not the pointing, but the four vector, let me call it. And the thing, because you contract with a unit, time-like unit vector, normal, this vector is causal and future directed. Well, if this observer is future directed or past directed, but the thing is that it's causal. This four vector tells you how energy momentum of the electromagnetic field propagates, uh, given an observer, and then you can decompose this vector in the in the quantities transverse to them. This one, the one that goes aligned with the observer, oh, I call it observer because it dictates which reference frame you use. It's always positive definite, and it's basically the energy of the system. And the other term is the pointing vector, the one that you use, the one that we learned from Griffith or Jackson book, and carries the information of how the energy, the electromagnetic waves propagate. So they did the same. They did the same. They for asymptotically flat, you have a normal, which is time-like, and well, it will be null, of course, for asymptotically flat, also for the Sitter works because it's time-like. And they rescale the Bell-Robinson tensor as well, such that this is finite at the conformal boundary. And then they just contract the Bell-Robinson with three of these normal because you have now four indices. And then you form this canonical vector, they call it the supermomentum vector. And again, when you expand this in space transfer to the normal, this W is called the super energy, gives you the super energy computed by Desert, by Bell, by Robinson. It's positive definite, and this is called the super momentum because it tells you it tells you how tidal force, the flux of tidal energy momentum to the boundary. Okay? For instance, in asymptotically flat space, you do it, for instance, in Bondi coordinates, and the the superpointing vector, this vector over here, its asymptotic value, it has these derivatives of the News tensor, the Bondi News tensor. This is in Bondi coordinates. And the only way that this full super pointing vanishes is if the News tensor vanishes. So this do not fully describe radiation, but it's a criteria. It's a criterion. So in Bondi, if you have zero News, then you don't have radiation. That's the criterion. Here, using this is analog if the superpointing vanishes. Now for ADS, it's a bit more subtle because the boundary is Lorentzian. So there is no preferred observer, causal observer, and the normal is space-like, of course. So what they did was to consider you need to choose all of the observers that are possible, all the frames that are possible. So you need to choose someone that is perpendicular to the normal and normalize, and then you contract the Bell-Robinson tensor with that observer. You expand, and the asymptotic value of this guy is called the superpointing vector, and they show that this actually carry information of gravitational radiation. The criteria is now that this is non-zero. Of course, this is zero. This will be there will be no radiation, and this translates into two criteria. First, that this calligraphic P is non-zero. This is we call it the radiative vector. They didn't introduce this in his paper, but what we did was just to contract the Bell-Robinson tensor with the space-like normal and expand that guy, and the asymptotic value of the one that is not proportional to the normal or not directed with the normal, we call it the radiative vector because it is exactly what appeared in their formalism. So this quantity must be non-zero, but also you have an extra condition that the cotton tensor of the boundary is not functionally independent, is functionally independent of the holographic stress tensor. Okay, so the cotton tensor. So notice that first, okay, if you write this vector explicitly, this was done in this paper by Luca, Sabrina Patersky, and Lisa Taur. It has this form at the boundary. So is this non-trivial contraction between the cotton tensor of the boundary and the holographic stress tensor? So the cotton tensor is like the Weil tensor, but in 3 dimensions. So if you are in 3 dimensions and you have a non-trivial cotton tensor, it means that you are in a manifold that is not conformally flat, just like the Weil tensor distinguish between conformally flat metrics in higher dimensions. Okay, so notice if this guy is zero, meaning it means that you do not have radiation. Okay, so it means that you need a boundary cotton tensor. You need to be in a non-conformally flat manifold. Your CFT must be in a non-conformally flat manifold, which means that you are breaking some numbers of conformal asymmetries. So you have less asymmetries if you want radiation, which is you can think of it, for instance, in flat space. This do not occur. You never discuss the boundary curvature when you do like Carrollian CFT, but that's because you have super translation. So you have a vacuum and gravitational waves pass enter to that vacuum. It will change the vacuum, but both vacuum will be related by a super translation. In the ADS case, we don't have super translation, so you need to break some conformal isometries due to the path of a gravitational wave. And as you need a non-trivial holographic stress tensor. Well, his web, of course. And this vector actually is conserved at the boundary. Okay, so I'm gonna use this radiative vector to describe holographic and describe it holographically using the fluid gravity correspondence. So what is the fluid gravity correspondence? It's a corner of the ADS-CFT, so which allows you to describe macroscopically your boundary theory in means of using hydrodynamics, using relativistic fluids, like a relativistic fluid. So what you do in the original paper by Juveni, Rangamani, and Benguala, they consider a black hole and they perturb the black hole, like I don't know, Schwarzschild black hole, will give you a thermal CFT in equilibrium at the boundary. So they made a perturbation in the long wavelength regime, low energy perturbation, such that the horizon, so they perturb the black hole and they start to solve order by order Einstein equation for the perturbations. And the perturbation, if they are small, they show that they actually correspond to the Navier-Stokes equation of a conformal fluid. So that is they map these equations, and this is known as the fluid gravity correspondence. Okay, so allows you to describe macroscopically. You don't care about the microscopic, like the constituents. You need like how the full behavior of your boundary is what matters. Okay, this is different to linear response in which you need a small amplitude. You don't care about the frequency of the perturbations, right? And you use Kubo's formula and compute like the the shear viscosity or whatever you're computing, the conductivity, the optical conductivity, or the DC conductivity. That's very well known. Here is the other way: you take small frequencies, and you don't care about the amplitude. It's for any value of the amplitude. Okay, so if modifications small modifications of the bulk, like if you perturb the horizon a bit, that will induce a temperature gradient at the boundary. And in hydrodynamics, to describe like dissipative, what you do is to use a derivative expansion of the velocity. So in fluids, you have a preferred vector, which is usually normalized. Well, that doesn't matter, but is time-like and is the eigenvector of the stress tensor, and that's the fluid velocity. So you do a gradient expansion on the fluid velocity, and that is mapped to these small perturbations of the bulk. Okay, and they use Edington-Finkelstein coordinate because you want to perturb the horizon to induce the formation of temperature. The horizon is a null surface, so you want to induce waves going into the horizon, and that everything is smooth there. So it's naturally describing Edington-Finkelstein coordinates. And the nice thing about these coordinates, uh, well, this coordinate is not Fefferman-Graham, but still you can define the holographic dictionary. You can map both gauges and use the standard dictionary that you know. But particularly in this paper by, well, David is one of the authors of this paper. Um, they they call this gauge the covariant Newman-Unti gauge because it's a relaxation of the Newman-Unti gauge in which you put this to one, this vector here. Well, all this coefficient to be one or minus one. And also because this describe, also done by the original authors of the fluid gravity correspondence, the boundary theory covariantly in terms of fluid variables. Furthermore, in this paper, they study the flat limit of this gauge. Because if you take the ADS manifold and you perform the flat limit in this gauge, the conformal boundary actually becomes the null infinity of the asymptotically flat space. Okay, so null gauges are really important because the Fefferman-Graham gauge is singular, of course, in the flat limit, so you cannot work on that. I'm not giving you references now, but there is a lot of progress on this. People is even taking flat limits of Witten diagrams or partition functions using null gauges like this one. So also the machinery of fluid gravity in this gauge is already given in the original papers. Okay, so you have a preferred vector that you can state. Any rank 2 tensor you can expand like this using this vector. Okay, like just what you do in fluid hydrodynamics. You know that this coefficient over here is called the energy density. Um, this is the local pressure of the fluid P. Tau is called the viscous stress tensor, and Q is called the heat current. So all the dissipative corrections are given in terms of tau and Q, which are both transverse to the fluid velocity, to this congruence. Because we are in a conformal fluid, you have this relation that the energy is 2 times the pressure. This is for this particular three-dimensional fluid. This depends on the dimension of this coefficient. And also another constraint is that the viscous stress tensor must be traceless. Okay, and if you have your stress tensor, which is conserved for our purposes, uh, you can compute the energy density and the dissipative corrections from it, just contracting with the velocity vector. Okay, so now you have this velocity field, this preferred. Uh, you can decompose. You can use the irreducible decomposition representation of the decomposition of his covariant derivative, and that gives you the kinematic properties of the fluid. So you have the shear, which is the traceless symmetric part of this. You have the twist, the vorticity, sorry, which is the antisymmetric part. Now you have the acceleration and the expansion. And all these quantities have a physical meaning in a fluid. For instance, the shear is how you deform the fluid in transverse directions without changing its volume. The vorticity is how it twists. The expansion is how the volume changes while the fluid expands, while the fluid moves, and so on. Okay. Now you can use Einstein equation and you start solve all the
Sorry,
variables.
Felipe, sorry for interrupting. So
Mhm.
what about vorticity? I mean, since you're doing this at the asymptotics, and asymptotics is a null hypersurface, I think you can
No, no,
show
but
for any null
I'm
hypersurface vorticity vanishes.
no, no, but I'm on ADS. I want to take the flat limit after.
Ah, yes. Ah, okay, I see. Yeah. Then, of course, vorticity is present.
Yeah, thank you. Sorry. Yeah. Okay. So now you can, the boundary data is not only G naught in this gauge, but actually also the time-like congruence, the fluid velocity. And then you solve order by order the coefficients, and because you have this preferred vector, you want to describe Weyl covariantly the boundary fluid, so you have a Weyl connection, and then you can solve the coefficients of the asymptotic expansion order by order up to the G3. Of course, G3 is not, I mean, it's given by this in terms of boundary data also. Okay, and where here you will see, you can see that you have the kinematic quantities that I wrote, but also this Ci start appear, and the Cs, the little Cs, are just the composition of the Cotton-York tensor. So the Cotton-York tensor is important in fluid hydrodynamics because describe dissipative corrections of third order. You decompose in terms of the fluid velocity, just like we did for the stress tensor, and then you contracting the indices with the velocity, the cotton density, the cotton current, and the cotton stress. P with two indices is the projector into the transfer space to the fluid velocity. And the thing is that, particularly for algebraically special solution of the Petrov classification, it, mean, it means a solution that has at least one multiple principal null direction, which is almost all solution but type 1. This geometry is fully Rousseau. You can, the metric takes a closed form. These solutions are shear-free, and there is a relation between the heat current and the cotton current, and the viscous stress and the cotton stress. So this is the generic form of any algebraically special solution in terms of fluid variables. This will be the reconstruction of the bulk in terms of fluid variable. So we are equipped now to describe the radiative vector that I showed in the beginning. So for the generic case, if you remember, you have the geometry and you have the stress tensor, so you have the radiative vector. For the generic case, the radiative vector takes this form. Uh, One, as you can see, is given in terms of geometry, in terms of cottons, and also in terms of dissipative vector and dissipative tensors. But if you see here, the first term is a bit particular because this is for the generic case. So the minimal condition for radiation in the general case, like type 1 spacetime, will be a solution that is dual to a perfect fluid living in a curved background, like this one. I don't know if such solution exists. I don't think so, but okay. This is the minimal setup for to have a bulk radiation in the bulk. So this will be the only case in which radiation in the bulk do not induce boundary dissipation. Okay, but for the algebraical special case, which is what I'm gonna work from now on, you need dissipation because there is no such term. If you have a perfect fluid,
Can I ask a question?
yeah.
Uh, I just lost the aim of your work is what is the aim of your work to find a criteria that there exists radiation in the ADS going to the boundary, or you want something more? You want to
No.
describe this radiation.
Yeah.
What is the I?
Yeah, sorry. Yeah, so no, the radiation criteria is given by Zenobia, and we are using it because we want to use holography for the case of negative lambda to describe this criteria holographically using the fluid gravity correspondence because we have more control of the boundary theory in that case. And also because we want to take the flat limit because we are interested in in asymptotically flat space that have radiation. And
Yeah, but what do you want? You want criteria in the safety side or
yeah,
in the
yeah,
flat
yeah,
space?
yeah, as
A
well, yeah.
criteria. You want to say when there exists gravitational waves or
No, yeah, I
uh,
want a criteria, and also I want to see if there is a how to map this criteria holographically in the boundary theory to see how the fluid changes when you have radiation in ADS and how it changes when you take the flat limit.
okay,
So
thank you.
yeah, no, thank you. Okay. Um, okay, so for this case, if you have radiation in ADS, the boundary fluid will have dissipative correction, nothing to do. And this is, so if this combo is, you still can have of course, a non-perfect fluid without radiation. If this full combo is zero, then there is no radiation. Actually, this occurs for instance, for the tau naught ADS spacetime, uh, or for the Kerr tau naught, in which you have a non-trivial fluid. I mean, it's non-perfect fluid, but they cancel. All the contribution cancel, and the radiative vector is zero. So that solution do not exhibit radiation, which you expect. Okay, what else we can learn from this criteria of radiation in terms of the boundary theory? Well, one important object that also appears in the description of fluid hydrodynamics is the entropy current, which is defined canonically like this. At first order in the expansion, well, if you consider zeroth order on the stress tensor, where T is the local equilibrium temperature. Okay, and this current basically, its zero component tells you the entropy density of the fluid, and its space component gives you the flow of entropy along that direction. And for conformal fluid, takes this particular form. Uh, this is in, if you don't have a U1, if you don't have more currents like U1 global symmetries, this entropy current looks exactly the same in the Landau-Lipschitz and in the Eckart frame. Okay. So what we can learn from this also, this, because entropy must always increase, you have this condition that its divergence must be positive or zero. If it is positive, it means that you have boundary entropy production. You have production in your fluid, production of entropy in your fluid, meaning that you are down in out of equilibrium, because when you have a field theory out of equilibrium, while you try to reach equilibrium, you will produce entropy, like when you put, I don't know, milk in your coffee. Okay, and this condition is usually used to constrain the numerical values of the transport coefficients, like the shear viscosity and so on. Okay, so we would like to know how radiation can be used to describe boundary entropy production, because we expect to have to have some notion of being out of equilibrium due to the gravitational waves in the bulk. And we actually found a relation between these two concepts in the bulk and in the boundary. So what we notice is that this vector that we construct by contracting the Bell-Robinson tensor with the space-like normals is also covariantly conserved at the boundary. So if you expand this vector, if you expand this equation will take this form. Okay. So recall that f can be written like this, which what is transferred to the normal, and the boundary value of this component is what we call the superpointing vector. Sorry, the radiative vector. So we expand each component, and then this equation takes this form. You have the radiative vector here. Now you have this super energy density. Its zero order appears here. And you have now a source on the right-hand side, which is the next to the leading order on the expansion of this vector, its radial component. You solve it because you know how, in terms of the stress and in terms of the cotton and the stress tensor. So you do an expansion. You found that the zeroth order is the holographic stress tensor square and the cotton square here. And the next to the linear order is more involved. So it's a contraction between the holographic stress tensor and the electric part of the Weil tensor. The next to leading order in the expansions, you see standard order 1 over r, and the next to the leading order, the 1 over r square, appears here, contracting this holographic stress tensor, and similarly with the cotton, but the magnetic part of the Weil tensor. Okay, that's the F1. The only bad thing is that we were not able to expand fully this equation because it's very, very long when you try to write in fluid variables. So if you have a non-trivial pointing, then this equation, the conservation of the F vector, sorry, that is covariantly conserved at the boundary, is mapped to this equation that we found, which tells you that the entropy, the divergence of the entropy equals this divergence of this theta vector, which we define here, is a quadratic vector in the fluid components, as you can see. You can have, like, for instance, be out have non-dissipation. This is for the algebraical special case. You can like have this to be zero, no dissipation, but you still have here something that is pure energy and pure geometry, these two terms over here. So there are signals to be out of equilibrium encoded on this vector. Okay, sadly, this is not the canonical form because in order to achieve that, we will have to expand this guy. We were not able to do that. But what we did was to test our, our equations using in known solutions. Okay, so just what we did was to describe bulk radiation using this new criteria in terms of the Bell-Robinson tensor, holographically, using fluid gravity and found relation between dissipative correlations and radiation, and also entropy production and bulk radiation. So known examples of radiative spacetimes are the accelerating black holes, which is like if you have a black hole and then there is a cosmic string and they touch, like a cosmic string touch the black hole horizon, this will accelerate the black hole away. And due to the acceleration, like literally move the black hole, due to acceleration, this will produce a gravitational radiation. And we wrote this solution into this covariant Newman-Unti gauge and compute the quantities. We have a non-trivial Poynting vector. These are the non-zero components. But we found that the entropy current is actually conserved. There is no boundary entropy production, which is really weird because this means that you are in a Mathéus thermodynamic path. So in a Carnot cycle, there is one that is a curve that is isenthalpic, but it still can be out of equilibrium maintaining the entropy constant. But I think, well, I will conclude later, but I think this is due because we have only the first order contribution. We wrote the entropy current in terms of first order. I think that if you go second order, there's nothing to do, but it's still peculiar. And another example is the Robinson-Trauman spacetime, which is the most generic like solution to pure Einstein, which is chair and twist free in terms of the null geodesic congruence, which is just dr. And it's written like this. You have this function, phi is called the Robinson-Trauman field, which is just a conformal factor of the codimension 2 metric because it's two-dimensional. Any two-dimensional manifold is a conformal manifold. So you found this equation, which is just the Calabi flow into this transverse section. And this is independent of the cosmological constant, so you do not care too much about the cosmological constant in this setup. This solution is really particular. You can glue it along the horizon with a Churchill spacetime up to a certain degree of smoothness. It's like 115 derivatives. It was studied a lot by Cristodulo. And this solution, if you do that and you take the infinite time, if you go to the future infinity, you will see that the solution reduced to the Churchill black hole. So the Churchill black hole is the final state of this. So you can think of this as an object that is emitting gravitational radiation. And at the very end, after all the gravitational radiation is emitted, and you end up with a Churchill black hole. Okay. And again, it's shear free and twist free. So the only non-trivial kinematical quantity we found is the expansion. We found that the radiative vector is non-trivial. It has this really complicated form. We cannot go further than this because this is a family of solutions given in terms of phi. So given a phi, you have a particular form. For instance, the accelerating black hole that I showed before is actually is a case of the Robinson-Trauman family. If you evaluate the entropy function just like that, like how it is, you find that it's proportional to the Robinson-Trauman equation. So this is on shell 0. And if you use our criteria, which was this long equation that we obtained from the Poynting vector, we obtain the same. That is exactly 0. So this is a highly non-trivial check. And this result was also obtained previously in this paper by Ciambelli, Petko, Predopoulos, and Kostas Tsiampos in 17. But there is a paper by Skenderis and Bakas from 14 in which they were trying to to study non-equilibrium conformal dynamics using a linearized version of the Robinson-Trauman, meaning that you have Churchill and you perturb axisymmetrically and with a small parameter. And they found that the entropy is you have a boundary entropy production, but they actually made an error in the definition of the entropy current. But then if you fix that error, you will find exactly that is zero. But in both papers, they were using just the entropy current at first order. So what we are going to study now is going to second order hydrodynamics and describe holographically to see if we can compute also these new transport coefficients, the numbers that appear in the definition of entropy current. It's way longer, but I think that there's going to be entropy productions. Otherwise, it's really weird. It will mean like almost any solution because we tested another solution that were like known for radiation for being radiative, and and still having zero entropy production holographically. So I think that if at second order that also happened, that we are learning something on the fluid gravity correspondence. Okay, finally, we studied the flat limit of this. All of this until now was purely DS. So the flat limit, what we did was to use a particular parametrization, which is called the Randers-Papapetrou parametrization of the boundary. So now you have a one-dimensional fiber and a two-dimensional base, space-like base, in which the boundary geometry you wrote like this. This is a general form in which all these functions omega VA and AAB, these tensors are are depends on all coordinates. And the thing is that this metric, when you take the flat limit, meaning L to infinity, is stable under Carrollian diffeomorphisms. And in doing that, the omega is a Carroll scalar, BA transform inhomogeneously and actually serves as an Ehresmann connection. And AAV is a Carroll 2 rank tensor, and it will be used as the metric of the transverse section. So we're using time-space splitting, okay? Of course, in the flat limits, the geometry is null. So in order to describe the manifold, you need not only the metric, but also the kernel. You need a null vector, okay? Which is known as the Carroll vector in Carroll holography. Okay, so Carroll holography nowadays is more and more understanding field theories on null, described on null manifolds. Okay, the dual of the kernel is called the clock form. It's just there is one connection, and and also we have a strong Carroll structure because the connection is ambiguous. We choose this splitting. We use the Levi-Civita connection of the transverse manifold, and also the one for the vertical fiber. So you have literally a split space and time, and you have to covariantly write all quantities for these two dimensions differently. Now we expand, like in these papers that I told you before. Like I told you that they exploit the flat limit of this metric before, and in the fluid quantities, the expansion look like this. So the energy and the heat currents are finite, but the viscous stressors have a divergent piece. So all these are called the energy density, the now Carrollian heat currents, and the Carrollian viscous stress tensors. Okay, so now the name Carroll appears everywhere in front. And for the algebraically special case, because we have a relation between dissipative corrections and, and cotton, right? This also occurs in the Carrollian side, where the cotton, you know how it is expanded because you know how the geometry it is. So C0 will be the leading order, the finite piece of the cotton density. XA will be the leading order, finite piece in the asymptotically flat, in the lambda to zero expansion of the cotton current, and XAB will be for the cotton stress. Now, if you plug this into Einstein equation, you will find that this equation takes this form for the fluid in terms of fluid variables, and they were mapped to the flux balance equation of Bondi Sachs formalism. So this is like the Bondi mass-plus formula, and this is the evolution of the angular momentum aspect in vacuum for the algebraical special. For the general, you will have sources here. They was shown in this paper. So there is a really nice map. You already start to see like a connection between celestial holography and Carrollian holography already using fluid gravity in the flat, taking the asymptotically flat space. So we have a radiative vector, which was described originally by Zenovia in the Bondi gauge. And he found that it's related with the derivatives of the News tensor. So now we are using the Neumann-Unti gauge or covariant Neumann-Unti gauge, which is better to describe Carrollian manifolds of the boundary. And we make an expansion, taking the flat limit of these quantities. If you take this vector with the index down, this is actually a Carrollian scalar. And we found that it has this form, so it's minus this number with the Carroll stress tensor squared. And its transverse component, the leading order, the finite piece, is minus this number times this contraction between the Carroll stress and the Carroll heat current. And this pair we call Carroll radiative scalar and Carroll radiative vector because they are actually a Carroll scalar and a Carroll vector, so they transform properly under Carroll diffeomorphisms. Okay. So you need dissipation. Remember that these guys were dissipative terms. So also in the Carrollian fluid, so let me call it fluid, we can discuss that. In order to have, if you start with a scattering processor or a gravitational wave in the bulk, if you describe the boundary theory using this hydrodynamic description, you need to have the dissipative corrections will appear into the fluid stress tensor, but it's not any, it's a particular kind of dissipation because you need the minimal condition is to have an stress, a Carroll stress. Because you can have a Carroll heat current but not Carroll stress, and these two will be zero. So we give a particular example in the paper. We did the Kerr-Tau-NAT, and that one is not a perfect fluid, has dissipative correction, but does not have Carroll stress. So that solution does not radiate from in the bulk. Okay. So if you compare with the Bondi formalism for the pointings, this means that you have like a Carrollian analog of the Bondi News tensor, because this guy in the Bondi formalism gives you like the time derivative of the News tensor, and this guy, the transfer component, gives you exactly this contracted with this covariant divergence of the News tensor. So now we are like reaching Bondi and Carroll formalism in terms of the fluid, in terms of the hydrodynamic description of the boundary Carrollian field theory. Why I don't know why we should, sorry, these are the examples. So the Kerr-Nat is non-perfect, but has non-strength, so this is non-radiative solution. We did it for Robinson-Traumann without cosmological constant. This is way more interesting because you have a non-trivial radiative vector, as you expect, because that solution is pretty well studied. We know that solution radiates, so it is consistent. So why I'm calling it fluid is just because I'm taking a flat limit of the fluid description of a CFT, or the Carroll limit of a field theory described using hydrodynamics. But to be honest, I don't know if we should call it fluid because, as I said from the beginning, there is no dynamics. So if you have no dynamics, then how you define temperature? If you don't define temperature, what you mean by hydrodynamics? But okay, that's something that people is studying from the last, I don't know, 5 years. One possible resolution is that people have actually found dynamics in Carrollian field theories because there are something called swiftons found by Genot and Salgado and Grumiller, I think. Maybe I'm missing someone, but they found that you can have in certain Carrollian field theories, I mean field theories with the ultra-realistic, you can think of them as the ultra-relativistic limit of a field theory, in which you can have a tachyon, but with energy bounded from below. So that's actually a well-defined particle, or can be used to define a particle, and then you can actually describe something like temperature, but there's nothing on that. It would be nice if we can say something about that in the future. Okay, just to conclude, we use the fluid gravity correspondence we just want to like close or make closer the gap between Carrollian holography and ADS-CFT, the flat limit of ADS-CFT. So we did it in the fluid gravity correspondence, and if that was done already in the past for like people like David, for instance, but radiative spacetime were not considered. And if you want to have a non-trivial uh, Carrollian, if you want Carrollian field theory that is non-trivial, then you need a new tensor. So if you want a new tensor from the flat limit of ADS, you need to have this non-trivial radiative vector as we show. So we describe everything in terms of fluid variables, and we made a connection with the boundary entropy production. That was nice. Still not that we still have zero entropy production in the known solution, so there's still something to investigate there. So this provides a macroscopic description of the dual Carroll fluid coming from the flat limit of ADS-CFT. And also in the paper, I didn't show it now, but we use the lambda BMS gauge, which is the Bondi analog is the extension of the Bondi gauge when you have cosmological constant. And we study celestial operators in this gauge, and we show how certain operators like energy detector operators that are using in colliders arise if you consider ADS radiative spacetime from the beginning. Some stuff to do is going to second order, as I say, to see if we can, if there is entropy production at the boundary or not. If there is not even at the second order, that will be very weird, and I mean that's a limitation of the ADS-CFT itself, I would say. Also, we didn't discuss the flat limit of this because this, if you remember, this equation gives you the criteria of boundary entropy production from more formalism. So what about the flat limit of this equation? Will this allow us to give an analog of entropy current or for a Carrollian fluid? That's not known. So also another thing that we would like to see is to describe memory effects purely in terms of fluid variables or in terms of the Bell-Robinson tensor. That will be neat. And of course, say something about the sitter, which is always very hard to do, but maybe there is a window for doing that using this approach. So thank you.
Okay. Let's everyone thank Felipe for a great talk. Okay, questions? So if there are no questions, I'll start. So just to make it more precise, so there should be memory effects in anti-de Sitter as well.
No, I don't know. I mean, if you start with the lambda BMS gauge, well, if you do it like a la Strominger, if you start with the lambda BMS gauge, and then you do the standard tricks, you take your shear tensor, decompose into electric and magnetic part. If you want the standard leading order, or the subleading memory effect, you hit it with that D, and then you start to see an integrate in time, and then you see that there is a memory associated with the square of the new tensor. If you do the same for the LMS, maybe there is like an extra piece appearing from the cosmological constant. People have done that in the sitter, but I don't know why anti-de Sitter. But no, what I'm saying is that start with anti-de Sitter, the fluid description, and then take the flat limit and see how the memory effect looks under fluid variables, in terms of the Carroll fluid variables. So, but I don't know if there is a memory in ADS. I wouldn't.
I have the following question. Can I ask? Thank you for your talk. You are dealing with some effective fluid description of a safety, as far as I understand.
Yeah.
Does it fluid have viscosity, and what is the relation with the limits which are obtained using the IDS black hole solution? Right, and it gives a viscosity of this of
Yeah, of the plasma.
n equals to 4, n equals 4 super young mu, it's like a minimal viscosity. What do you have for viscosity in your case?
Yeah. So the viscosity are the transport coefficients. So you can read them actually from the entropy current. That's how you do it, like in the standard fluid hydro in the Landau-Lipschitz book. But when you do that in ADS, so in ADS you have this gravity, and they show that the ratio must be less than 1 over 4 pi. And I think quark-gluon plasma has shown that this is true. Phenomenological agents have never violated the bound. That for us in the flat limit, the theory is a Carrollian theory. So I don't know, then you will need a Carrollian plasma to test such, but yeah, that's a good question. I don't know if it makes sense.
So does your fluid have analog of viscosity?
Well,
And does it have a limit?
yeah, the thing is, take the Carrollian stress tension. I think there is no much. That's a really good question.
Oh.
I will look for it. But again, it's called fluid just because of that. There is no notion of dynamics, so no temperature, and okay. But thanks. I will think about transport coefficient.
Okay. Questions 1. Questions 2. Okay, if there aren't any more questions, then let's thank the speaker again. Okay. Well, see you around, and thanks again for the talk.
Yeah.
Thank you.
Thank you. See you.